very, very pleased to welcome Professor George Koutsantonis, who has agreed to give our Chemaraderies lecture this evening. He will be talking on the adventures in molecular photochromism applied to materials. Professor Koutsantonis is a synthetic chemist with an interest in functional materials that contain metals. He's a graduate of the University of Adelaide, where he obtained his BSc Honours and PhD degree. He undertook a postdoctoral position at the University of Kentucky, and after a fruitful period in the USA, he returned to Australia on an inaugural ARC postdoctoral fellowship at Griffith University in 1991. He was appointed to the staff at the University of Western Australia in 1995, where he still remains. In Perth, he established an independent research program in organometallic and inorganic chemistry applied to materials, and he is a recipient of the RACI Organometallic Award and the RACI Leighton Medal. So please join me in welcoming Professor Koutsantonis.
I'll leave it for a moment. Thank you, Keely. It reminds me I need to get a new photo. I don't think I'm going to talk about a complex with a metal in it this evening, so I better strike that off too. And yes, I've been at UWA for a long time, and I was interested in your reflections, Stuart, about joining in 1970. I joined in 1984. Ferdy's been a member for a long time. And I contrast that with a conversation I had with a younger colleague who was not coming tonight, saying to me he's no longer a member of the RACI. And I think that's one of our greatest challenges, is getting hold of the younger people. Okay, now, earlier this week I wondered why the hell I'd agreed to give a talk in the middle of exam marking, but I did, so I will. We've been interested in photochromes for some time now, for various reasons. We wanted to apply them to materials, and I'll take our own particular bent towards what materials we're going to apply. So I thought I'd start out and give you, well, it's unashamed plug for the Australian Journal of Chemistry, because I'm also co-editor-in-chief of that, and I'd like to encourage people to publish in that journal if they would. But firstly, because I always run out of time at the end, I really do need to thank all the people that's helped do some of the research that I'm going to talk about towards the end of the talk. And of course the people that give us the money, including those far-sighted Danes that wanted to give us money here in Perth. We'll take it. We'll do something with it. Right, but and the other thing I want to reflect on this slide, when I look at this and compare it to slides similar to this that I prepared when I still call them slides, of course, when I was younger, there was far fewer people on it. And that just reflects the fact that science has become an interdisciplinary, multi-collaborational exercise, and therefore my advice to people is to, starting out, is to create those linkages early on in your career. I want to talk about photochromism. Photochrome exists in two different states. The word, of course, is Greek, which is appropriate, certainly I'm giving it. Comes from the word phos for light and chroma for colour, of course, and that's where it comes from. And you can define them as two different states that are actuated by a wavelength of light, and they give different spectra, or absorption spectra, as a consequence of the two different forms. And we'll look at some of the types of molecules that have come about as a consequence of these. One of the effects of this transition is often that the one or other of the photoisomers has interesting properties. You can affect dipole moments, you can affect absorption, you can affect conductance, a whole range of things, and this is why they're interesting, in my view anyway. There'll be a short tutorial at the end of this talk on, quiz. Notice a couple of my second-year students here tonight on what these photochromes are. Now, you could have two types, a T-type or a P-type, and they could be both positive and negative. I won't read out what a positive and negative one is, but a T-type is where you've got a low potential energy barrier between the forms, and your metastable B collapses back to your A, whereas a T-type is you've got, a P-type is where you've got very stable photoisomers that actually require a further wavelength in order to switch back. And you start to think about some of the applications of these. I'm going to go through every one of these, of course. No, I'm not. This is my unashamed plug. We wrote if anyone's interested in the history of photochromes or indeed the fundamentals that one might apply, there's this wonderful series of articles in the Australian Journal of Chemistry where we create a primer on a particular subject, and we've written one on photochromism. Like I said, I'm not going to go through every single one of them, but I'm going to go through some of them. One of the first examples that was recorded was, in fact, taking a solution of anthracene, shining light on it, crystals fell out, of which are a dimer, and you can reverse that by heating those crystals in the solution. Now, you moved on, and this benzaldehyde phenylhydrazone goes red in sunlight, but then fades back to its colourless, another colour in the dark. So there are some examples. We got to, where am I going here? Right, now, this example is an unusual one, but the only reason I put it up is because at this point in 1899, this effect of switching between two states was called phototropy. And Mark Wald, in fact, coined that term. And of course, now we realise we use that term not for photochromism, but in fact for things that grow towards the light. So there's a different meaning for that. Now this was an example, one of the first examples of a P-type photochrome in which this fulgicide was able to be converted to, various isomers. Now, where's my pointer going? There it is. Excellent. So this was a P-type photochrome and one of the first examples. Now, by about 1929, the first review was written on these particular types of molecules, and what the outcome of that review was some of the problems with these photochromes. The number of times that you cycle is an important aspect of this, because if they cycle too many times, they tend to, even minuscule side reactions tends to break down the effect. And this term was called fatigue for obvious reasons, and that was highlighted as part of that. When the solubility of azobenzene was attempted to be calculated from photochemical experiments, solubility experiments, they noticed the cis-trans isomerism of this particular molecule. Now, if we move on to Hirschberg, an Israeli chemist, that showed that this molecule could, two states, a quinoidal state or something like that in this particular state, and he coined the term photochromism. So that's where it is now. I want to talk about spiropyranes and their ringed open isomer mericinin. It's a part of the Fischer-Indol synthesis. They're relatively easy to make. But also, these were some of the first compounds that were used in those photochromic lenses in glasses that people use, right? So, but also they're used as dyes. I heard about natural dyes tonight. Well, this is an unnatural dye, as a lot of them are, of course, and an important aspect. And partly I'm putting this up because we tend to play with these quite a bit. We've also tended to play with these dihydropyrenes a lot, which have advantages and have disadvantages. And again, these have been developed since the 60s. And in fact, most of the photochromes that we play with nowadays tend to have been discovered after about 1950. Erie, Japanese chemist, looked at these diarylethanes with various bits of spaghetti around them, but nonetheless they go through coloured and colourless forms, and these are, again, P-type photochromes. So in that instance, you don't have to worry about thermal reversion back to the starting point. So that's an important aspect. And these are heavily used in chemical research. And I'll finish off with this last example. Ben Feringa and his colleagues won the Nobel Prize in 2016 for, in his case, molecular machines. But these crowded alkenes, in fact, with a axis of chirality, and were able to be utilised to move about. Now, I don't want to focus too much on these particular types of diagrams down here, but I wanted to focus on the important aspects of the rearrangements, right? So this requires a quantum of UV light, and of course it ring opens, the carbon-oxygen bond is lengthened, opens, and you can stabilise the mericyanin form as a consequence of putting electron withdrawing groups on here, which makes sense. Excuse me. Ultimately, when you look at this, this has to go from a cis alkene to a trans alkene, and there are a number of pathways that have been looked at in terms of this, and we won't go through all of this, it's going to take too much time, but you can have a singlet pathway or you can have a triplet pathway. Now, I haven't talked about some of the things you need to talk about when you're looking at photochromes, things like quantum yield, photostationary states, a whole lot of other jargon. I refer you to that excellent primer in the Australian Journal of Chemistry if you want any more information in that regard. But the hydropyrenes are fascinating, and I first learned about them sitting in a chair at a conference on Heron Island where I thought I was having a good time, but in fact I was actually getting ideas for research grants, which was useful. I had a good time as well. But they intrigued me because they're a negative T photochrome, right? They're coloured to begin with. These things are some highly coloured materials, and they open to this relatively colourless cyclophanediene form. And one of the real problems with them is the low quantum yield for the ring opening, and that's a consequence of the number of pathways or states that are accessible. And you can either talk about a diradical approach at breaking at this particular junction, or you can talk about a zwitterionic approach. Nonetheless, that's because of all of these different pathways, they think that that's why the quantum yield is nowhere near what it could be. Diarylethenes, again, you can have a variety of conformers, and really that's all I wanted to point out here. You can cycle between these two states, and a lot of the materials applications is a consequence of that, right? And the overcrowded alkenes fascinate me, but some of the features are this stator that's symmetrical, and this asymmetrical rotor that you can then activate with different wavelengths. And in fact, Feringa has used these in terms of creating molecular machines, which I suppose is an interesting academic exercise. But then again, we never know where interesting academic exercises end up. I can think of a number of those. Right, so there's a variety of different states associated with that. The point of these last two slides was to show you that there's multiple pathways that you need to think about when you're trying to use these particular materials, these particular chemicals and materials. Right, now this are just some applications from the literature, right, to show you that there are real applications for these types of materials. There's been a D flip-flop using this particular fulgicide, or fulgimide rather, where you use different laser wavelengths to provide information and complex logic operations. You've got different lasers, 1064 nanometer, you've got a 355, 532, and you've got a variety of second and third harmonic generating materials that give you those wavelengths, and you can actually have these quantum states or these states that address these things. Now this is an example of the overcrowded alkene. Right, now I'll just step you through some of the features, and I suppose those of you down the back can't see a damn thing, so I apologise. I thought they'd be bigger than this. Now this molecule looks a treat to make. I'm not sure I'd like to, but nevertheless. they're able to. They can deprotect this particular sulphur to form the thiol, treat it with base, that then forms a thioacetate, and then they hit it with a wavelength, and it swaps positions and then puts the acetyl group here on the amine instead. Neat little reaction. I'm not sure where you get to it with, but it's an example of what one might do with these types of photochromes. Right, and cartoons tell a lot of stories. I love the papers I get to review where this cartoon tells you everything you need to know. We don't have any evidence for what's in the cartoon, but just read the cartoon. Anyway, that's just the beef. Photopharmacological approaches. This is based on a azobenzene, right? So we've got this pyrimidine that's got antibacterial properties. In this particular conformation, it's not active. You hit it with its quantum of light. It's able to then provide its payload, whatever you want to call these things. I think that's a sexy term for it. And it has antibacterial approaches. And my last application, apart from the ones that I want to talk about that relate to us, is in fact these MOFs. And those of you that know me, I don't like MOFs, which is molecular organic frameworks that are made either of molecules or sometimes metals and three-dimensional networks that people talk about engineering the crystals to form. But this is an interesting example insofar as it's got an amine with various nitrogens here which can interact with carbon dioxide. In this form, the transoid form of the azobenzene that's here, and you hit it with UV light and it flicks to the cis form and therefore doesn't leave enough room for the carbon dioxide to be interacting with the nitrogen and therefore releases the carbon dioxide. And of course, you know, carbon dioxide is of particular interest to a number of people in various industries. Okay, now I'm going to indulge myself and talk about what we do along with colleagues at UWA and colleagues elsewhere. Small ensembles, individual molecules to replace CMOS technology seems far-fetched. My own view is that it's got to be a complementary melange of all of these different types of things. Single molecule devices, great test beds, but I think three-dimensional arrays of molecules will in fact be where we go with this, along with various other types of materials. I really do want to point out the fact that it's a highly interdisciplinary endeavour, right? And, you know, there's physicists, there's chemists, there's mathematicians, there's a whole range of people that have looked at molecular electronics. Mark Ratner said that, you know, you'd need synthetic chemists, experimental physicists, physical chemists. Do we have any of those left? Yeah, I think we do. And theoreticians, and we don't have any of them. All of whom have faced and are facing several challenges. And I'm not in the same league as these people, but if you can't make things, then you can't do anything with them, right? So you need to be able to make things, and that's really the point I wanted to make here. And if any of you are interested in where the Australian perspective in molecular electronics is, again, another excellent article in the Australian Journal of Chemistry. Okay, Gordon Moore founded a little company called Intel, died this year, unfortunately, and his prediction back in 1965, the number of transistors on a chip would double every 2 years has been about right. And we're just getting cleverer and cleverer and cleverer, but we're reaching the limits of how clever we can be with existing CMOS technology. So people started thinking about, can we use molecules? And if you really want to talk about those in Feynman's lectures, there's room at the bottom, is a place that a lot of people go here. But certainly the potential for looking at molecules in devices was brought about by a number of advances. Long history, field effect transistor was patented in 1930. You know, the point contact transistor in 1947, they went on to win the Nobel Prize for that. Bottom-up molecular engineering, here's Feynman's lecture in 59, and a variety of other things that have happened. I think for our purposes, although I remember reading about it in the 80s, I didn't actually understand what it meant for chemistry, was the invention of scanning probe microscopy, you know, STM and those sorts of things. That, in fact, has revolutionised this area, and it's important to recognise that. Right, so they got the Nobel Prize. Oh, where's my pointer gone? Here we are. Got the Nobel Prize for this. Atomic force microscope, and then we started to look at various other things. More components, Intel, the first microprocessor, 32 bits, clock rates. Lithography is where it's been in this industry, and we talked about lithium plants costing $2 billion, new semiconductor, new chip producing factories cost in the order of billions of dollars as well. So there's a lot of money invested in this technology. And some of the issues have been heat transfer. They don't run at the same sort of clock rates that they should. There's a couple of ways of doing single molecule experiments. This is the electrochemical STM that we have at UWA. Where is he? He runs, there he is down the back. And Alana, they do a lot of that. I look at it and say, isn't it shiny? But clearly there are a couple of ways of doing this. Mechanically controlled break junctions. You've got a solution of your molecule. You've got a junction here. Wire-like, you bend it, you break the junction, and then you try and put a molecule across that. Right? The advantage of this over the other technique I'm going to talk to you about, this scanning tunneling microscope break junction, you have gold tip, you jam it, not quite jam, but you put it into the surface. You've gold surface in a solution of your molecule, you pull it up and you go fishing for a molecule. More often than not, you get one. And then we measure the conductance of that molecule to a point where the tip breaks off. Right, so, and you have to do that experiment thousands of times for it to be statistically relevant. And you don't select your data, you just use what you get. And this is one of the first examples where thiolbenzene was measured in the conductance of that. Right, so people have done molecular wires to the death, and you know, you think about all sorts of things, conjugation, all sorts of things. Even an alkane will conduct, you can conduct through the sigma pi manifold, the sigma manifold of that particular molecule, right? So there's no such thing as something that, wow, conduct poorly. Like I said, wires are good, but there are a whole range of other things that you want to do with molecules in this space. You want to have molecular junctions, you want to be able to measure them, you want to have molecular arrays. Clearly, if you want to have microelectronics, you need to have field effect transistors. You might want to do spectroscopy, thermoelectricity and spectroscopy. But the space that we've been working in is looking at making molecular switches, right? You want to control the movement of charge through these molecules. And I love this journal, the Journal of Extreme Manufacturing. But nevertheless, and this is one of the photochromes I talked about, the diaryl ethenes, and you can have a variety of these. And ideally, you want to be able to rectify current as well as switch current, and you want to have transistors as well. So what I'm going to talk to you about now, hopefully for not too long, is the use of some of these photochromes as molecular switches. Right, and the hope was that you could obtain two different states, and the conductance of those states would be driven by light, and therefore getting down the heat load, where you've got fast photo-driven processes of high quantum efficiency, and hopefully that would lead to something interesting. Now, as I said, I was sitting on the beach in Heron Island, great conference, lectures in the morning, lectures in the evening, do what you like during the day, and I'd seen this lecture. I thought, oh, I'll do this. I'll try and make one of these switches when I get back. I knew it was a good idea because someone else had thought about it too at that point, and had made this dihydropyrene. Now, what I should tell you about this particular version of this dihydropyrene is that you can make that in good yield in a significant number of steps, which I'll show you in a moment, but I won't go through every step. And then you can, if you like, decorate the periphery of these molecules with groups. Now, what I didn't tell you about, when I should have, is that in order for you to get a molecule in a molecular junction, you really need to have coordination chemistry happening, right? You need to have some sort of donor atom that can interact with the gold. Sulfur's a good one when you're talking about gold. Nitrogen's effective. There's a variety of them out there, right? So what we try to do is engineer molecules that have this, say, nitrogen there, put it in a junction and measure the conductance. And Thomas von Lausky was able to show that you could switch conductance of these particular molecules. Unfortunately, Thomas died, can't remember how long ago now, through an unfortunate illness. And he had Wei Jinghong, who was working with him at the time, has taken the cudgels up in China now. Now, our ideas here on the right, on your right, what we wanted to do was to put a dihydropyrene in this particular molecule. We wanted to connect it at these positions rather than at these positions, partly because we wanted to ensure that we got the molecule sitting up and contacting. We weren't having it lying down. How do you know? Well, you can look at break-off distances and things like that. But and hopefully that the R groups here, either side of that ring, flat ring, would stop it from lying down and into the pi cloud interacting with the gold surface, because clearly that sort of thing could happen. Our grand visions of putting a metal complex here. Why? Because I'm an inorganic organometallic chemist, and that's the thing I do. Alkynes, well, I played with those for a long time, and so we didn't want to reinvent the wheel here. We wanted to use existing methodologies to make the sorts of things that we were interested in using, and all of this fitted the bill. What we needed to do was to make this type of starting material. That's good. Well, that's the talk over now. I know what's happened.
You got it?
I think so, yeah. Suffice it to say, it's an interesting synthetic endeavour to get to the compound that we needed to get to. I'm not going through every step here, and this is not reinventing the wheel. This synthesis was known, and we adapted it to our use. And I'm not going to go through every particular step, but we did a lot of optimisation. I wanted to point out, in fact, we finally got to the compound that we wanted, which was protected alkyne. But rather than getting a good yield, we got 10%. And that's partly because this byproduct. Okay, we tried 4 or 5 months worth of optimisation. We couldn't get any better, so we forged ahead. There wasn't any point in wasting any more effort. We had something in hand. We were going to go forward. Yes, I know 10% is cringeworthy, but nevertheless, we had to move on. Just an aside, this is a crystal of that compound. And this is the advantage of keeping your eyes open. The person that did the melting point, yes, I still do melting points, noticed that it decolorized, but didn't melt. What's going on? We could have ignored it, but we didn't. We found that, and in fact a colleague at UWA did the solid state crystallography of this at different temperatures, and it undergoes a phase change, and ultimately we start to see loss of electron density around certain positions of this. The next slide tells you what actually happened. I won't go through too much of it. But what we knew from the literature was that certain groups here would actually start to move out and in fact move their way around the ring. And of course, once you move these two off, you lose the dihydropyrene and you start to form pyrenes. And they're not photochromes. Right, so this was a disappointment, but also it was satisfying to get to the bottom of what had been known in the literature, but a complete pathway hadn't been known. The working title of this paper was The Stiff-Legged Chicken Dance, as it moved across the pie cloud. And it ended up being called A Merry Dance Across the Pie Cloud. You've got to have interesting titles for papers, I think. My late colleague, Alan White, wanted me to stop me from using an analogy about packing in a crystal as a bucket of dead lizards with tennis balls. The conformation it adopted depended on how hard you shook the bucket, which I thought was a fantastic analogy for different crystal polymorphs. He didn't win. I got it in. It's published. You can go look for it sometime. Colours, fantastic. This is what got me into chemistry in the first place, right? This mauve pink colour is this compound. This blue purple colour, and of course I'm red-green colourblind, so take that on notice, is that colour, right? So we had the compounds in hand. What do? Great. This is an example of the results you get from these experiments, right? They're two different representations of the same data. These two traces at the top show the conductance data. I won't go into the units, suffice it to say that these are conductance peaks at different potential difference or bias between the electrodes, right? At 100 millivolts, you get fantastic two-dimensional plots that shows the stability of that molecule, this one, in the junction out to about 1.8 nanometers, which is about the length of our molecule. Fantastically stable. Similarly for the other one, right? And we were really excited at this data. And as we changed the bias between the electrodes, our peak conductance started to go down. And we thought, fantastic. What we've got here is a bias modulated ring opening of our photochrome. We've done what we set out to do. Nah, we hadn't. What the theoreticians, this is why you need theoreticians, right, Peter? You told us that it wasn't possible in the terms of the electric fields we were producing at these biases for that to be ring opened. So that's got us stuck for about a year and a half trying to work out what happened here. I know, a year and a half. You know, in academia, if you're not publishing papers, you get sacked, as a number of my colleagues had been. To make a long story short, what was happening was the stability of the junction was decreasing at higher biases, and the probability of forming a junction was less, and that was being reflected in these traces. Great. Not good for us, because what we wanted was a bias-controlled ring opening. Now, you're all saying to me, weren't you talking about photochromes? What happened to light? They don't switch. These molecules do not switch with light. And please don't say to me, have you tried this? We've tried everything. This is why it took a year and a half, right? We tried everything. And if we'd read the literature a little more carefully, we'd never have put alkynes on there, right? Because that was our problem. We were no longer in the space where we could attack that particular photochromophore, if you like. So that was disappointing. Not all was lost. I'm not going through all of this. We like to do spectroelectrochemistry, right? We'd like to look at the electrochemistry of a molecule while then observing what's happening using either infrared radiation or, in fact, UV visible light in order to tell us something what's going on structurally. And what we found was in fact that on the second oxidation of these particular compounds, we got a ring opening. This is almost as good as what I had before, because if you can now use current to switch your molecule, then you're in the same boat as CMOS technology pretty much, or traditional microelectronics. The problem we had, of course, was we didn't know what the UV visible spectrum of the ring open form was, and that's where we got Peter Spackman to calculate, in fact, what it was and compared it to what we found experimentally, and they matched relatively well. Right, so that was that. The last story I'm going to tell you about, how am I going for time? I don't want to bore you too much. Spiropyrans, a lot easier to make than dihydropyrenes. They do switch. They switch in a number of different ways. If you can add acid, then the acid protonates the oxygen and it ring opens. If you can then hit it with various wavelengths. I'm not going to talk about the earlier work we did with collaborators from here. What I want to focus on is the various generations of molecules that we looked at. Now, clearly one of the problems with having electronics with a spiropyran is, in fact, the large conformational change. Right? What are you going to do? Start pushing the electrodes up and down? You don't want that. Nevertheless, so we had 3 generations that we looked at. We looked at ones with alkynes, we looked at ones without alkynes, and then we said to ourselves, let's move the conduction path right out of there and just put the photochrome on the side and look at conduction through here. Right, so now the earlier work I told you about, we got conductance. We were able to switch conductance using acid, and we were able to cycle backwards and forwards. And of course, we have these various states that you go through. You protonate, you hit it with light, it goes to the trans-isomer, you deprotonate, it goes to this, and it reverts back. Here's some examples. Again, the chemistry here is not trivial, but we're able to make these compounds. And really what I wanted to do here was hopefully show you what's going on. Right, now, the blue torch, flashlight, is a UV light. The red one is a visible light. It's cut down to 18 seconds, so keep watching. Right, UV changes colour. You add acid, changes colour. UV light changes to another colour. You add base, it goes back to that colour and eventually becomes colourless. Right, so they're the various states that we could go through. We had a number of addressable states. Okay, so first generation, 2 types. When I first drew this, I drew the cross-conjugated type and said to the student, make it, it's conjugated one. I got it wrong. So we had to go back and make the proper conjugated one. Not really seeing much here. There are some peaks, but we've got 2 forms, low conductance, high conductance form. You add acid, it opens. You try to add base, you lose the high conductance peak. Ultimately, you're forming salts in there. The Faradaic current becomes an issue. We went to these, got nothing. This lump just tells us that we're not really having any conductance features, right? So all we've done here is take the alkyne out of the picture and put the contacting groups on the end. And within the limits of the detection of this particular instrument, we're not seeing any conductance peaks. Then we went to this thing, and bugger me, we didn't get any conductance again. We're starting to get a bit desperate here. We're not seeing anything. Now, you can rationalise this in terms of course, that once those rings rotate, then they go out of conjugation. The closer they rotate into conjugation, then you would expect to see peaks. And that's what we think is happening here. Then we did these 2 compounds, and in fact, they showed, albeit low conductance, they showed proper conductance peaks. Compare these to the ones I showed you earlier, right? They're not as good. but they are conductance peaks. And ultimately, then we thought, right, again, these are our collaborators in Liverpool, took our molecules, put them in the STM, and then looked at them without UV light and with UV light and got a change in conductance. Remember, these are log scales, right? So there are significant conductance differences here. And we were able to demonstrate this in situ in the instrument, right? And this was, we thought, pretty cool. For both the addition, or both light activated or with acid activated. And I'm not going to go into a long diatribe on this. This is pretty much my last slide in terms of the chemistry. But the upshot of this molecule that I'm showing you here is the switching happens here. When it switches, it actually impacts the movement of those aryl rings, and they move into beta conjugation when it's open. That's the whole effect here. It's got nothing to do with the it's got something to do with the switching portion. They just move into conjugation and give us a peak that's different or more with more conductance. And we called this electrosteric switching, and we recently published it. And you know, the theoreticians were invaluable here. I won't go into all of these. There are technical terms for photoresonances and things, and we could demonstrate what it's coming. But the upshot is that these molecules are able to mediate the conduction as a consequence of moving those rings into beta conjugation. What we're trying to do now is actually lock that conformation by putting alkenes in the way and making sure they're in conjugation and see what effect that has. And I want to finish with a couple of things. Reg, not that I ever met the man, he needs to be acknowledged for the work he did in dihydropyrene chemistry. In spite of his trying, he never was able to come up with a structure-function relationship for the ring opening of dihydropyrenes, pyrenes rather. One doesn't exist, but without the work that he and his group did over the years, we wouldn't have been able to do anything, and I think it's important to acknowledge those people's contributions. And he knew when it was time to retire, which is something that I'm looking at, what I'm going to do. And of course the group and you guys for taking time to listen to my ranting. Thank you.
Thank you very much. Perhaps we could have a quick question. Does anybody have a burning question before the break?
Yes.
George, any organic compounds superconduct?
Yeah, superconduct. Actually, we were talking about that today. We were hoping to get a superconducting magnet at liquid nitrogen temperatures. That'd be nice. Look, I don't know the answer to that. I mean, clearly there are conducting organic compounds. Whether they're superconducting, I don't know. In terms of, you know, a low temperature or high temperature superconductors, which is I think the point you're getting to. There are certainly a variety of conjugated polymers that conduct, but not superconducting that I'm aware of.
All right. Well, maybe George will stick around and answer any other questions that you might have. Please join me in thanking Professor Koutsantonis this evening. As a token of our appreciation.
Thank you.
Thank you.